This is video 232, and the objective here is to understand how a graph behaves at the roots, zeros, or intercepts. Our secondary objective after that is then to be able to graph them. So I think you have some great tools to graph these functions. We just want to make sure we understand what happens at each of the zeros. So here's a key factor here, the multiplicity. The question with multiplicity is, here's what multiplicity means. It's basically asking how many factors of the zero are there. So if you take a look at the two examples here, the first example has even multiplicity for all of its zeros because this factor, x minus 2, occurs 2 times. And so does this factor. It occurs 2 times. Now when we look down here, we see the factors occurring an odd number of times, 3 times or 1 time. So these different multiplicities mean something different about the graph. Because it occurs twice, remember we know that we can sketch a graph and get it started by knowing that it's going to have a 0 at 2 and 1 because of the factors here. But the question is, what does it do at 2 and 1? What does it look like? Does it go through? Does it bounce off? And that's what you need to know about multiplicity, is that it does affect what happens with the graph, and it causes, if it has an even multiplicity, the graph will bounce off of the 0. If it has an odd multiplicity, it will cross at the 0. So let's take a look at this graph. You have all the tools you need now to graph. So we know that these two mean that it's going to bounce in both of these spots. The question is, will it be below or above the x-axis? So one other thing that we want to find is, remember, our y-intercepts. So we have our x-intercepts and we need our y-intercepts. So our y-intercepts occur when x is 0, and that's going to occur at -2 squared, -1 squared. I'm just plugging in 0 for my x value here. And it looks like I'm going to get 4 times 1, or 4. So that means my x-intercept's up at 4. The last thing that I'm going to check is the end behavior, just to make sure that I have the right graph here. So my end behavior, remember, depends on my a value at the front. And if I think about foiling this entire thing out, I'm going to have a positive x to the 4th power at the front, because there's nothing negative that would multiply by that highest power of x to the 4th. So I know that this graph, I know multiple things about this graph. I know it's going to cross those 3 points that I have graphed over here. The second thing that I know is that it's going to end going up. And since it's to the 4th power, I know that it's going to end, that it could potentially look like this, or maybe it looks more like a quadratic like that. But I know that it's going to start and end going up. So now I'm ready to graph this. It's going to look like this. If I want to be a little more exact, I could plug in something like 1.5, and make sure I can see that it actually peaks there, or maybe it kind of flattens out. Maybe it's really low-lying in here. But I do know that it touches at those 2 spots. So I have a nice sketch using my major points and understanding what's going on. Is it going to bounce, or is it going to cross at those different points? And there's my sketch of my function. Now, when I look at the odd multiplicity, once again, it's still crossing, it's still touching, going to be for sure touching at 2 and 1. And if I plug in 0 to get my y-intercept, I'm going to get f of 0 at, let's see, it'll be -2 to the 3rd and -1. So it looks like it'll be at +8. So up here at 8, it's going to cross the y-axis. Since both of these have an odd multiplicity, it's going to cross at these. So I know that it's going to go down and cross at the 1, and apparently cross again at the 2. Notice again, though, that I have a 4th power, 4th degree polynomial, just like my previous one. If I were to FOIL this all out, it would be a positive 4th degree polynomial. So once again, it could easily take this W shape, or it could take more of this parabolic shape, or it could look kind of funky and do something weird like that. So it could not hurt to plot a couple more points. So I'm going to plug in 1.5 into my calculator just to see what's going to look like at that point. I could also use my graphing calculator to graph it and find some key points, but let's see, 1.5 in for the calculator here. It looks like when I plug in 1.5, I get approximately negative 0.0625. So it's really tiny. Sorry about that, negative 0.0625. So it's really quite close. Now if I plug it into my graphing calculator as well, I see that the graph is kind of staying right next to the axis here. So I know it's going to cross, but it kind of just stays and then crosses over here. Okay. So remember, you want to connect it with as smooth a line as you can, because we know the parabola has a nice smooth curve to it. But we've graphed the major points, and we've seen we have a nice sketch of our graph, so we understand what it looks like at the beginning and the end. So let's take a look at one more thing to help us understand these graphs and to make it easier to graph in the long run. So we're going to skip this one. We're going to look at this one. This is an important piece to understand about the turning points, and some of you might remember this from the past. If f is a polynomial function of degree n, so remember that means that the highest power is n. Remember, degree is power. So it's saying that this function has something with x to the n in it, and then maybe all the way down to x to the first plus 5. I don't know, something simple like that. But we know for sure that the highest power is n. Then the graph of f has at most n minus 1 turning points. So for instance, if this was a times x to the 10th, then I know for sure that it has 10 minus 1, or 9 turning points. So it has one fewer turning points than it does power. At most, okay, that's a key word. It doesn't have to have 9 turning points, but it would have at most 9. So if you're graphing this and you're thinking it has more than 9 turning points, that's a problem. And to understand a turning point, it's simply where it changes from increasing. This graph is increasing, then it turns to decreasing. And so those are turning points here. It's just like you might think of it, where the graph turns and goes the other direction. Okay, a turning point can be subtle, or it can be pretty drastic. Okay, but a turning point is a turning point. So this one would have a degree at most. A highest degree would be x to the 3rd here, because it has 2 turning points. Okay, the x to the 3rd would be the smallest degree. Excuse me. It could be x to the 5th, because this one could be a 5th power polynomial, but it would have x to the 3rd would be the smallest degree. This could not be an x squared function, as we all know. Okay, so keep those things in mind to help us decide what the graph looks like. We're going to look at one more example from start to finish. Here's the basic steps to graphing. You should have already done a bunch of these for assignment 2-3A. You should have determined the end behavior, found the x-intercepts. Now you should know how to find multiplicities. You should have been able to find the y-intercept. The symmetry, I would take a look at your graph for that. There's no easy way to decide that each time. Simply plot the points and double check your turning points to make sure you have the right graph. So let's take a look at graphing this one. Determining the end behavior. Since it's x to the 4th and it's positive, it looks like it will start and end going up in the positive direction. So I know that in between there something might go on, some wiggly lines in between there, but for sure it will end going up. Now we want to find the x-intercepts. So we're going to take a moment and factor this. Okay? It looks like, since the x squared is here, I'm seeing something like this. X squared minus 1 times x squared minus 1. Take some practice to be able to see those quickly, but that's one thing I see with factoring. I also know x squared minus 1 can be factored into x minus 1, x plus 1. And so I have a couple of double multiplicities, because this one appears twice and this one appears twice. So I know it's going to turn around at positive 1 and negative 1, and I'm going to scale my axes a little bit so I can have a nice complete graph. So it's going to turn around at those points. In order to know if it's going to, I kind of know it's going to be above, because I know it's going to take this form like this. I just need to know where is that y-intercept. This one actually will have quite a bit of symmetry. Let's take a look at the symmetry that it will have. It's going to have a y-intercept, so when I plug in 0, I get 1, which is really easy to see from this form. So I'm going to cross up at 1. It will have a y-axis symmetry. Okay. As we can see here, it's mostly because of all these perfect squares, these two perfect squares that create this product. Now I'm ready to graph. I have some bouncing going on at my two intercepts, and I have my y-intercept right in the middle. So this is what you're going to be doing to complete your problems. Definitely use your graphing calculator to check your answers and see if they in fact turn out to be the way that you're predicting. But try and graph these by using your tools that you've learned here.